Well, let's get started now. Thank you so much for joining us for this digital workshop. We're going to be talking about software development toolkits for additive manufacturing. So with me today, I have the pleasure of speaking with Richard Baxter, the head of sales and marketing from Polygonica MachineWorks, as well as Elad Schiller, the co-founder and CTO of Castor. I'm Jonathan Gerwa from TechSoft 3D. We make engineering software toolkits, or SDKs, and we provide those to over 700 different 3D engineering companies building engineering software, many of which are building software for the 3D printing space. Elad is here to showcase both the Hoops Exchange toolkit that I'll be talking about today, as well as Polygonica from MachineWorks. So we're going to talk about those two toolkits, introduce you a little bit to our companies, TechSoft 3D, as well as MachineWorks, and then be able to have a partner presentation here from Castor. So we look forward to that. And again, if you have any questions, please put them there in the QA panel. We'll get to them at the end of the presentation. So a little bit about TechSoft 3D. As I mentioned, we make software development toolkits. We're really excited to fuel innovation out in the field of 3D engineering. We've been doing this for over 25 years, working with companies small and large, providing them technology like graphics and data access and analysis tools and simulation. And it really is exciting to see what you do with our tools. So we're just very happy to be able to supply this technology to you. And move the industry forward when it comes to innovating. And that certainly is the case here in additive manufacturing. So in addition to Castor, we have a number of different partners that are making 3D printers and printing software, and are very excited to be working with them to help them bring the next generation of software to market. This is just a selection of some of the many different partners that we have, different software companies that we provide technology to. In addition to these, we have a number in building and construction, mechanical CAD, PLM, metrology and CMM, shipbuilding, and anything really in the 3D engineering space that deals with 3D technology that isn't in, let's say, entertainment for the most part. However, Unity and Epic Games also are using some of our tools. But let's focus on 3D printing. That's why we're here today, to talk about supplying technology for the 3D printing space. And I'm going to start with a pretty controversial statement. We all know STL. We've used it and probably had the headache of using it as well. And I want to focus on data access specifically in the next couple of minutes here. And start with STL is dead. Well, it isn't really, because we still deal with a ton of that data, but there are issues with STL files that we're continuing to run into. And a couple of them here, it's a tessellation-based file format. So we're dealing with triangles that are coming from many times curved surfaces. And they're just an estimate of what that exact surface is. And if we want to be very accurate, and if that's critical for us, we want to get closer to that surface. Now, that's possible with increased tessellation. It might not be available. And obviously in our STL file, we have to go back to the original CAD file. But that approximation sometimes can be a problem for us. Another problem is it doesn't really contain the rich descriptions of materials, both from like a material of what we're going to build this out of and all the metadata, but then also just the color, translucency, and then additional material properties when it comes to some of these more modern file formats and the way they describe surfaces, surface texture and whatnot. So we also need a file format or access to that additional material data and metadata. We aren't just interested in dealing with single parts, but many times these parts are part of a much larger assembly. And STL files really aren't designed to represent all of the nuances of what an assembly might be, with different configurations and different associations and instancing. It's just a soup of triangles. And then lastly, there's additional metadata within many manufacturing systems that help describe what it is we want to build, with geometric dimensioning and tolerances, particularly product manufacturing information. We see some here in the bottom right image. So this is information that allows us to actually design the part and then manufacture it to that design. STL files as well, they don't really they don't encapsulate that information. We have to go searching for it elsewhere, and it doesn't follow the model throughout the life cycle of manufacturing. So some issues with STL, many of these have been solved already for many years within native CAD file formats. And so we would like to talk about Hoops Exchange, which is a CAD data access toolkit that gives you access to and solves many of those problems. So this is a software development toolkit from TechSoft 3D being used in many applications today. Many of those who we saw the first set of logos there in 3D printing. And it does have access to not just STL and being able to read that into your application, but many other file formats. And we're able to give you rich data from those files if it's present as well. So that's information like tessellation, the boundary representation, or BREP, this geometric dimensioning and tolerances, or PMI, product manufacturing information. It gives you access to the assembly tree and how these different parts are related to one another, as well as the material definitions and additional metadata. So let's dig into that just a little bit more. And first, talk about what do we support when it comes to bringing in CAD data to your application? Because now more than ever, if you're providing a solution for 3D printing, your users are going to be getting data, or they have data from a variety of sources. There is a loss of information when it goes to STL, and some problems can be introduced in that translation. So the closer you can get to that original CAD data, the better. And so we support over 30 different file formats, particularly in the engineering space, formats like JT and NX from Siemens, CATIA and SolidWorks from Dassault Systems, all of your standards like STEP and IGES, as well as some of your visualization standards like GLTF, U3D, OBJ, of course, we have STL in there as well. The benefit of using an SDK to read data from a variety of sources is, instead of writing these file readers yourself or interfacing with different SDKs or different APIs from these different vendors, really you need to create and only create a integration with one API. So you're creating an integration between your application, Hoops Exchange, and you get all of this data all at once. So it's a many to one. You don't have to maintain these relationships with other APIs to get the data, nor do you need on your user's machine a copy of, let's say, CATIA or SolidWorks and driving that reader out of that application. So it's a standalone set of libraries. They don't need these CAD applications to be running. We reverse engineer these file formats and provide that rich data to you so you can make intelligent business decisions. So let's dig into some of the different things that we provide, particularly for 3D printing. The first is tessellation. So many of our workflows are still optimized for triangles. Many of these file formats that you just saw, they have the triangle representation embedded in it, so we can quickly read the data, read the triangle data from these different file formats and quickly be able to provide that to you for both visualization and then eventually for outputting to the printer. However, if there is boundary representation or BREP data available, so that's the mathematical representation of these surfaces, we're able to retessellate either at a much higher level, so you get a much closer tessellation to the surfaces, or at a lower level if you want to simplify the model. And we also push to applications like, or SDKs like Polygoninca that can further help you simplify, fix, and heal your model as well. We'll be talking about that in a minute. As well, as part of this tessellation, we provide a number of other control parameters that allow you to create tessellation specific to your workflow. We did talk about BREP. So even though many of our workflows are optimized right now for triangles, kind of the future of what we're seeing software being developed is looking at these actual mathematical surfaces, the BREP surfaces themselves, and being able to print directly from them. And so having access to those arcs, curved surfaces, the cylinders, the cones, the spherical surfaces, people are able now to make use of that and make manufacturing decisions off of that. So we do also provide that as part of the API if it's part of the file. And many of these modern CAD files from the major vendors like PTC, Dassault. They provide this data to you. The other part of this is not just providing the triangles, but the BREP, but also all the manufacturing information around the parts as well. And so when an engineer actually designs a part, they're embedding additional geometric dimensioning and tolerances or product manufacturing information. We see another example of that here about what is not just the hole diameter, but what tolerance do we have for that particular surface, and can we meet that with the manufacturing process? And this is something that's been utilized by the subtractive industry, the CAM industry, for many years. But now we're seeing it being used in the way in which we now print them in the additive space as well, is can we hit those tolerances? And if we can't, well, then we have to go back and talk to the design intent, talk to the designer to see if that is actually going to invalidate the part, or it might require us choosing a different method of manufacturing, either a different printer itself with a higher level of accuracy, or some post-processing milling. And I think Elad is going to talk about that a little bit. We'll see from his demonstration. But all of this product manufacturing information, this GD&T, it's available both in a visual form. So here it's rendered for you here, so you can visually interpret it and make decisions from it. Or you can even interrogate the data structures in what we call not visual PMI, but semantic PMI. And that is a set of data structures that you can query within your application and then make automated, or let's say intelligent and guided business manufacturing decisions. And we're seeing that for the different platforms that are doing quoting. So maybe a user uploads a file to a cloud application, and it automatically looks at some of these dimensions and tolerances and sees if can we actually manufacture this? Is it within our ability? And then provide an intelligent quote based on that. Many of these parts that are being built, they aren't just being used by themselves, but they're part of a much larger assembly. And so being able to provide access to that in an intelligent way is really important. So how does this part fit in within much larger assembly? So through the API, we can give you access to that. How is it instanced? Are there different configurations where parts are swapped in and out? If it's a very large assembly, can we just load the assembly information without loading every single part and giving you all the, let's say, loading all of the BREP or all the tessellation in this, what we call a shattered mode or a delayed mode, where you just get, here's the assembly, give me the information now for just one particular part. So you get a lot of control over how you load the data within your application as well. So an example of this, here is an application, GrabCAD Print, that is, you're going to see an example of loading an STL file, as well as loading a SolidWorks assembly of several parts. This is an earbud assembly, like a Bluetooth earbud assembly. And so it's loading both of those files. And you can see in the left-hand corner of our build plane, the STL file, which is really just a collection of triangles, as well as the disassembled and now reassembled SolidWorks assembly here on the right. One thing you'll notice is that there's no material information here in the STL file, but we're able to extract that from the SolidWorks assembly. It's also just a collection of triangles, and when we try to apply a color to that, let's say another material we want to print in, that's a real advantage of this application, being able to print in different materials and a large number of colors that are selectable. We can only apply it to the entire model, not an individual part. But the SolidWorks assembly, it maintains the integrity of each of those parts in different space, and it allows us now to instance it, in this case, select a particular part, and then apply a specific color to that. And so this is really two of the different parts of Hoops Exchange we're seeing, well, many we're seeing integrated here: assembly, navigation, we're seeing material information being loaded. We're also seeing the tessellated data coming from the SolidWorks file. And so we've been focusing on just Hoops Exchange. That's our SDK for reading CAD data. into your application. It's part of a much larger suite of tools at TechSoft called the Hoops platform, which includes graphics. And so many times you don't want to just load data, but you want to be able to see it. So there's a direct integration with two of our graphics engines, Hoops Visualize for desktop graphics and for mobile, even AR and VR, or Hoops Communicator. And this is graphics for the web. So we're able to render data loaded from Hoops Exchange into any modern browser. And then we also have Hoops Publish, which allows you to create reports, intelligent reports, in the way of 3D PDF is one of the primary outputs of Hoops Publish, as well as 3MF and as well HTML, standalone HTML. So this is the Hoops platform. Again, we're focusing mainly on Hoops Exchange today, bringing data into your application and then fixing it with Polygonica, which we'll see in just a minute. But then another area where we see a lot of interest in and application in 3D printing is that of simulation and analysis. And so I did want to talk briefly about a very common workflow that we see and some other toolkits here at TechSoft under the Citron platform. So this is another product line we have at TechSoft. So Hoops is engineering data and graphics, data exchange and publishing and graphics. Citron is particularly for the CAE space for simulation and analysis. So a common workflow is you bring in data using Hoops Exchange, goes to Polygonica for fixing and preparing for 3D printing. However, it also prepares a 3D mesh that we can give to Citron Mesh that creates a uniform mesh that we can then use as part of a static solver. Given boundary conditions, we can solve and see how does this do under certain loads, and do we need to change our design in order to support the design intent for that particular part. And then Citron Envision is a desktop and web graphics toolkit for viewing this very specific CAE data. And so that's another graphics engine, but specific for visualizing analysis data. And we're seeing more and more of simulation and analysis in 3D printing. It's an exciting space right now for us because we want to be able to not have to design parts that fail. We want to take all that we learned from the subtractive space and be able to apply it here in the additive space. And this has been part of the product life cycle for many years, where we, before we even building something, we make sure that it's going to fulfill our needs. All right, lastly, we have Hoops Exchange and Polygonica. So we saw that on the first slide, or the last slide. Hoops Exchange does have an integration by way of sample code with Polygonica. Richard's going to talk about that and how Polygonica is used to heal and Boolean parts together and really prepare your model for 3D printing. But we do have some sample code that allows you to integrate these two very quickly and get working, passing data from Hoops Exchange to Polygonica and back. I'm more than happy to work with you if that interests you and you're interested in these two toolkits. This is part of our sample code that we can share with you. And right now at C++, we do have some sample code for C#. And it supports stuff like materials, colors, assembly, and then also this bidirectional mapping of surfaces, parts, and other aspects of the data. So that's an introduction here now to Polygonica. I'm happy to introduce Richard Baxter, Head of Sales for Polygonica MachineWorks. I'm going to stop sharing and allow Richard to share and talk about, now that you have your data, what do you do to prepare that for printing? And Richard, if you could unmute yourself, that would be great.
Yeah, apologies. I did know that I needed to unmute myself, but could not find the button anyway. Despite that, my name's Richard Baxter. I'm Head of Sales and Marketing at MachineWorks, but I've been a software engineer most of my career, and I'm still doing software engineering with Polygonica, mostly writing demos, including the demo program I'm going to show you in a moment. So we're on LinkedIn. Please follow us. We're pushing out updates through that. It's probably the best way to stay informed of new things that are happening. Okay, so what's Polygonica? It's a software library. It's written in C, it has a C API, and we provide C# and .NET wrappers for it. We support it on Windows, Linux, and Mac OS, and we have customers using it, integrating it into desktop applications, cloud services, and increasingly on-premises deployment where people are actually using it to sort of automate parts of their in-house workflows and things like that. We've more than 50 OEM partners using Polygonica, and that's growing pretty rapidly. Polygonica, it's primarily focused on polygon meshes, and we also have quite a lot of operations relating to sort of 2D and 3D polylines, which we term curves. So there's things like imprinting curves onto a surface, then offsetting them, and similarly a full 2D sort of hatch and infill pipeline. And there's also a full point cloud processing pipeline in there. So it's a toolbox of really well implemented, multi-threaded, performant, and most importantly, supported algorithms. And I think that last bit's really, really important. If you encounter a problem, or if you get some crazy mesh from the wild that isn't working, instead of you having to spend weeks trying to fix it, you throw it over to us, and we'll use our skill and expertise and hopefully provide a solution. There's tons of functionality in there now. From the top left is stuff that's been in there, being developed continuously for nearly 30 years now. Automatic healing, 2D and 3D Boolean operations, to newer stuff down on the right, such as 3D medial axis and deformation compensation for additive manufacturing. Where did Polygonica come from? Well, we didn't come from additive manufacturing. Our involvement and focus on additive manufacturing is kind of a coincidence or an accident. We're actually from the subtractive industry originally. So the company's name is MachineWorks, and MachineWorks is a software component for CNC material removal. We started developing that in 1994. The company's based in Sheffield in the UK. Everyone comes into the offices where I am now in the picture. And in 2014, we were acquired by Heidenhain. So Heidenhain is a very large German manufacturing company. They make a whole bunch of things, but specifically CNC. They're one of the leading manufacturers of CNC controllers. And so they acquired the company to put MachineWorks libraries on every controller that they sell. And actually now they also add Polygonica and use Polygonica for some functions in their controllers also. Just a quick word about MachineWorks. So MachineWorks is, at the heart of MachineWorks, is a very fast polygonal BREP Boolean engine. So what I mean by this, by BREP is boundary representation. So we have a boundary that encloses solid material, and that boundary has connected faces. The difference with the CAD engine is that those faces are planar polygons. That's the primary difference. And they're planar polygons because it's way faster, and it needs to be faster to meet the demands of the subtractive industry, CNC material simulation. That was started in 1994. It's now 2023, so nearly 30 years, and MachineWorks remains the primary engine in use in that industry. But the point about mentioning all this is that Polygonica and MachineWorks share the same code base. So the healing and Boolean engine in Polygonica comes from MachineWorks. And some of the newer algorithms we're developing for Polygonica going back into MachineWorks. So there's a synergy between the two products there. And these are some of our software customers that use MachineWorks. So Dassault, Autodesk, the large number of CAM brands that are owned by Hexagon Manufacturing Intelligence. Similarly, Sandvik, who owns Cimatron, GibbsCAM, iCAM, etc. And similarly, on the hardware side, there's a large number of major machine tool manufacturers who develop their own software to go alongside their machine tools. So companies like DMG, Mori, Akuma, and Makina all use MachineWorks. On the Polygonica side, about 50% of our customer base is additive. So we've got Octon, 3D systems, so 3D Sprint, 3D Expert using Polygonica, Stratasys, GraphCAD Print, Jonathan's mentioned. The whole suite of products provided by Desktop Metal, and that includes now EnvisionTech, or eTech as they're now known, and their factory software. That's all based on Polygonica or uses Polygonica. Castor, who Elad is going to talk to you about in a moment, Velo 3D, Intech Additive, Next to 3D, Zortrax, and also CAD's Additive, which they make a product called AM Studio, which was developed in conjunction with SLM and is now an independent product. So that's resold by Hexagon and by quite a number of other companies. And then on the CAE side, also worth mentioning, ANSYS use Polygonica in quite a number of their software solutions. So within additive manufacturing, I kind of split the usage up into three or four really, if you count CAE. So there's print preparation, there's loads of useful stuff in there for that. Less well known are 2D operations for build processes, so hatching infill, medial axis, slicing, etc., etc. We have a major metal printing company developing a new build processor based on Polygonica, and they told me just this week that they've actually started printing parts using that, so that's really, really great news. And also the final category I tend to think about is what I've called cloud-based auto quoting, and that covers a whole range of different services, if you like, but the general commonality is that somebody somewhere uploads some kind of CAD part or an STL file or whatever up to a cloud server, and then automatically some form of information is given back, typically a quote as to how much it's going to cost you to actually get this thing printed. Yeah, and finally, Polygonica is used by CAE simulation vendors, including ANSYS. I mean, this is becoming increasingly important in 3D printing and additive manufacturing, and it's typically used for preparing the mesh prior to CAE remeshing, and sometimes for post-processing after topology optimization or types of generative design, etc. Okay, so I'm now going to move on to demo. So this demo is called, this GUI is called Polygonica Demo, but it's not available. You know, we don't give it to anybody, we don't sell it. It's just a demo program, but it gives you a nice overview of what you can do with Polygonica. So I've loaded in a small STL. At the top right here, it's 60,000 faces. These traffic lights are telling us it's not watertight, it's got self-intersections, it's not manifold. And that's what these red colors mean. So red is self-intersecting. Green is open edges, so that's an edge with only a single face attached instead of two. And purple in Polygonica language is non-manifold, which means an edge with three or more faces attached. If I just turn off that error display and just show you the mesh, then you can see what's happened here. We've got, it's a bit weird, but we've got a sort of double mesh, two meshes sitting on top of each other, you know, and at the blend here, it's sort of one's poking through than the other one. So clearly, you know, a bad state of affairs and not usable. So I'll click the healing tab. I mean, Polygonica's got a whole ton of healing functionality I'm not going to talk about in this webinar, but I'm just going to click the automatic heal function, and then bang, 1.6 seconds, everything's green, and we've got a nice closed watertight manifold result that you can then throw into your slicer or whatever. But we're talking here about Exchange, so let's load in an actual CAD part. So this is a SolidWorks assembly, and I'm going to load it into this demo using the Exchange Polygonica bridge code that Jonathan was talking about. So that code is tessellating it, converting the tessellations to Polygonica, and in this demo, I've just thrown all those parts. I haven't kept the assembly structure. I've just thrown it all into one single STL bucket, if you like. So there are obviously going to be mesh errors. So I'll click healing and let Polygonica heal that. That's going to take hopefully about 10 seconds. Just a word, I'm running this on a 4-year-old Core i7 laptop. So it's probably not even a mid-range game machine these days. So it's nothing, there's no special hardware here. Okay, so I'm showing the facets. So one nice thing that Exchange has done, or the Exchange Bridge has done for me, is it's kept back pointers to the original BREPs in the Exchange database, BREP patches in the Exchange database. So that means I can select them. So I select a triangle, but then I go back to Exchange and I can say, well, you know, tell me the triangles in this in this BREP patch, and so I can do that here and here and here. So that's a nice thing. And then what else can we do with these? Well, let's try remeshing them. How about that? So we'll just do a local remeshing of these 4 selected BREP faces. There we go. There's a nice remeshing, but you can see we've lost the boundaries between those BREP faces. So I'm going to undo that and select the faces again, so I don't remesh the whole model like I did last time. And this time click Keep Boundaries. So it's just remeshing those 4 BREFs, but you can see now there's a nice clean boundary there, there's a nice clean boundary there, there's a nice clean boundary there, and that's all because we've kept the structure from, even though this is a dumb polygon mesh, we've kept the structure that's been provided to us by the Exchange bridge. So that's really neat. But what we're doing additive here, so let's hollow this thing out and add a lattice. So I'll just click that and just get that going. So this is doing a whole bunch of Polygonica operations under the hood. So it's doing offsetting. So it's offsetting the whole model inwards. It's then doing a Boolean subtraction of that to create the hollowed model. It's then creating a bunch of cylinders and spheres to represent the beams and nodes of the lattice. And then it's throwing everything into one big multi-Boolean operation. It's like a scene-based Boolean. So you just throw thousands of parts at it and do all the Booleans in one go in an optimized way. And so at the end of it, we'll get a hollowed out part. And it's explicit geometry in that if you want to say pass this to a CAE remesher or something like that, you can do. All the joins, all the intersections have been evaluated. And it's done that in 33 seconds. And if I just make that transparent, and we can see, you can see the lattice inside it. And I'll just clip it. So where are we? 2D profiles. There we go. So I'll just do a section plane through it just so we can see the inside a bit better. And you see there's a lattice, and it's done that all nice and quickly, and you've got a lattice through there. And if I click fill solid on, you can see there's also the hollowed out bit. So finally, we'll slice this. Let's do 1,000 slices in Z. So again, Polygonic's got a pretty advanced slicing. If you've got printers with high tolerances, large print areas, then Polygonica slices, you know, it's going to work for you. It's been optimized for that kind of stuff. And there we go. It's done that in 4.5 seconds. And again, if I show a section through, you'll see it's also sectioned all that lattice. It's sliced all that lattice stuff on the inside. Okay. So I'm going to load in a 3MF part now. So Polygonica doesn't support 3MF loading natively, but we do provide some example code that reads and writes to 3MF, so you can make use of that. What's interesting about this part is it uses the 3MF beam lattice extension, so it defines beams and nodes in parametric form. What we're doing when we're loading it in here is we're actually instantiating all those as meshes, and then again doing a massive Boolean union of all the instantiated beams and nodes with the mesh geometry that's in the 3MF file, and creating the final explicit geometry of the part while we're loading it. So it did that in 17 seconds. So this part actually has 32,000 beams in it, which I had to double check because I didn't believe it when I first saw it. But I mean, it's a tiny 3MF file because all the beams are just represented as start and end points and radius of cylinders, etc. But you can see Polygonica has created the explicit mesh geometry from that really quickly. But we can also do another variant of the same kind of thing. We'll load this 3MF file in, and then we're going to slice it. So instead of doing a 3D Boolean union to create all that explicit geometry, what we'll do is we'll slice it all and as its separate components, and then do all those unions in 2D. So we'll just get the final slices rather than having to create the full 3D instantiation of the object. And there you can see, I mean, that did that in 4.5 seconds. I mean, I've only created 100 slices here. It would obviously be slower if you created a reasonable amount of slices, but you can see that's done that really quickly. Okay, next one, I'm going to load a Creo part. This is again loading in through Exchange. Now you can see that there are some mesh errors here. So we're just using the default Exchange tessellation for visualization here. Exchange has an accurate tessellation that produces watertight models, but I want to show Polygonica healing, so I'm not using that. So we can fix that. Bang, that's nice and fixed. And let's look at some wall thickness analysis. So show wall thickness. So Polygonica is Polygoninca is basically doing an even sampling of points across the surface of the mesh. So it's independent of the mesh tessellation. And then it's measuring the thickness of all of those and then coloring them based on a threshold. So if I drag this slider up and down, I get more or less areas where it deems the walls are too thin. So you know, that's probably about right. So this lettering is obviously too thin for the printer, etc. And we've also we're about to release gap thickness, which is a similar principle, but it's actually measuring the gaps between faces as opposed to the thickness of the solid material. So in this case, if let me just make that 3, then we can see these holes are obviously below, the diameter is obviously less than 3. If I make it 6, then more of these holes are, you can see here, more of these holes are less than 6. And then I'll just, for the sake of showing off, I'll just, there we go, make it a bit bigger, and then we can see that this pocket, the width of that pocket falls below the 12 threshold. So useful sort of printability analysis functionality there. And we've also got surface fitting and feature detection. So surface fitting is the idea that we fit, or we do a best fit of portions of canonical surfaces like spheres, cylinders, cones, toruses onto the surface to give you analytic information. So for example, if I double click this, I've got a cylinder, so I know the center and axis of the cylinder. Now, obviously, if your data has come from a CAD model via Exchange, that's pretty pointless because you can get that information really accurately via Exchange. But if somebody's giving you an STL file or something similar and you need to kind of reverse engineer it, then this information can be useful. I will say, though, that if you've got freeform surfaces, this is not going to do a great job because you'll be trying to fit portions of cylinders. It's not going to automatically fit a NURB surface to your freeform polygon mesh. It will try to fit cylinders and toruses and things, and you'll end up with lots of tiny surface patches, which won't be very useful. But in terms of sort of finding out about what's in a polygon mesh part, it's quite useful stuff. And the other important point is it also works with laser scan data. So it's tolerant of noisy data. So it can really help with reverse engineering laser scans. We also have feature detection, which was originally put in for 2.5 axis machining, so generating can cycles from prismatic parts. We do have customers now using it for additive. And so we're putting more effort into making it more robust with respect to sort of mesh irregularities and things like that. But the main difference with the feature detection is it's finding you things like, so it knows that this, for example, is a pocket, and it knows all the sub-features within the pocket. And similarly, it knows this is a hole, but it knows it's got connected features within that hole, and it knows things like chamfers, radii, chamfers, fillets, etc. So that's the main usage for that. So two more demos. Quick demos, and then I'll hand over. So simplification is really widely used by our additive print preparation customers. I'm going to show it on a laser scan part simply because it has more impact, but it works perfectly well with CAD parts, very well with CAD parts. So here we've got a typically overfaceted result from a laser scan. If I click, I'm going to simplify it to an error tolerance of 0.1. So what that means is the resultant part will be no more than 0.1 units from the original, and it's done that in 2.4 seconds. It's reduced it to 14,500 polygons. It was originally 600,000. So if I'll just undo that, and then you can see that it was originally 626. I'll just do the simplification operation again. So it's very fast, multi-threaded, and gives you a very accurate result so that you know that your resultant part is within the tolerance you've told it to be, which is really important. And finally, some new functionality we added last year in Polygoninca 3.2, and this is mesh deformation compensation for additive manufacturing. So I've loaded in 2 meshes here, and I'm just going to set this thinking and then explain it. So the grey mesh is the design part, and the brown mesh is something we've mocked up to simulate something that might have been deformed during the printing process. So it's drooped in Z, and it's also shifted in XY. I actually didn't put a very good angle there, but you could possibly see in some of these places here that it's actually shifted in XY as well. And so you could create this deformed, drooped part by doing a laser scan of a printed part, or you could do it. It could be the results of CAE analysis. What Polygonica has done is take the two parts and compute a deformation field, which is a bunch of control points and a set of vectors with a magnitude in the distance, that will allow you to morph one mesh into the other mesh. So if I just look down from above a bit better. So let's look at that. We'll just look at that bit. So if I click deform, that's now applying that deformation vector, and it's moved the gray part onto the brown part. So what you would want to do for compensation is you'd want to go in the reverse direction. So in this case, we're using the same vector field, but just applying it in the inverse. And you can see that's lifted it off the part and moved it away. So for small deformations, at least, the idea is that when you print it, it will move the part to be in the correct location. You'll get the correct printed part. Okay, so that's the end of my section. Now I will try to stop sharing. Okay.
Excellent. Thanks so much, Richard, and sharing all that, well, not all, but many of the new things of Polygonica as well. Next up, let's look at your demo is nice, Richard, but a prettier application from a lad from Castor. We're very interested to hear what you have to present to us.
Thanks, Jonathan. Can you hear me all right? Great. And just let me know if you can now see my screen. Great. So yeah, thanks for having me here. Greatly appreciated. I will start by saying that we would probably be very far from where we are today without the help of Polygoninca and Hoops Exchange, though the two libraries that we are very heavily using. I will give a quick 5-minute intro about the company in case you don't know us, and then I will jump into a demo and try to explain where we are using the tools from TechSoft and Polygonica. So we're Castor, and our main mission in life is to help manufacturers by helping them find the best business cases to pursue when it comes to additive manufacturing in end-use manufacturing parts. So basically, if you're looking into manufacturing a machine, it can be with hundreds or thousands of parts at once. You will upload to Castor, the list of parts. It can be 100,000 of parts, or assembly with a huge amount of parts, and we will tell you what can be printed, what cannot be printed. Where is the opportunity when it comes to finances? Does it save money? Does it save carbon emissions? Does it save lead time? And we'll help you optimize it to the best technology, best 3D printing technology and materials. So 2 words about us as a company. We are on the road for over 5 years. We are almost 30 employees sitting in Tel Aviv. We are backed by both financial VCs and industry leaders in AM. And my co-founder is Omer Blair. He originally from Stratasys, and we know each other for 20 years from the Army. So yeah, we work with, when you have clients in many industries, including AM, defense, aerospace, automotive, etc. And the reason that they are using us is that, like us, they understand that the challenge of choosing the correct manufacturing method in the last few years has become such a challenge that needs a data-driven approach. And that is because of new breakthrough technologies out there that you might not understand as well as you understand the technology using for the past 20 years. It's also because the supply chain isn't, is disrupted often, and you might need option for onshoring. And sustainability is something you need to take into account in almost any decision you make. So a data-driven approach is what's needed in this case. I skipped a slide showing that we also work very closely with many partners in the 3D printing industry, whether by integration or white label. This is very important for us as a small company. So how does it work? Basically, you will upload a full assembly to Castor. We will explode the assembly into the individual parts and give you an assessment on every part. It will be a financial assessment as well as a technical assessment, material, geometry analysis, cost analysis, and in the end, we'll also give you a stress analysis that will help you understand if the forces applied will work in an anisotropic material environment. And the holy grail is to find parts that can be redesigned for additive. So there are many companies out there that help in redesign for additive. We are good at finding out of thousands of parts, those parts that will give the most impact if you decide to go and redesign the part. 1 second. So this one example that I'll give here, and then I'll go to the demo. This is a part we found for HP. It's part of a huge 2D printer. And what's nice about this example is that we were able to save 75% in cost. And that is due to the fact that these parts were manufactured separately. And when they were manufactured as one piece in additive manufacturing, it gave them many advantages, including cost, weight, and reduce assembly time. So I think I'll dive into the app right now. I'll start by showing the upload page of Castor. This is one of the ways that people use Castor. The other one is via integration. So for instance, if you have Teamcenter, this can all happen automatically or a different PLM. Everything can be analyzed according to preset rules. But basically what we need is 3 inputs. We need the geometry, the quantity, and the original material you were planning to manufacture the part with. And I think that in this part, Hoops Exchange is a real game changer, because what we can do is basically write, give us any native 3D CAD file format and we will crunch it. And this is actually true. As of a year and a half ago, I think we have no complaints when it comes to formats. And this is a huge win for us. And not only that, we also are able to extract from these files data that saves the user from bringing extra inputs, PMI data, such as material, matching data, etc., etc. This is priceless for us. I will say that we also support 2D drawing. This is a proprietary algorithm that we have, where we understand the 2D drawing and assess whether this can be a good candidate for AM. But we do heavily use Polygoninca here, because once we understand the 2D drawing, we need to recreate this 3D file or something near it in order to give our assessment. So we use that Polygoninca for that. So this is how the results of analysis looks like. This is an assembly with 130 parts. And what we do is we categorize them into printable parts, printable with minor changes that you should probably still assess, unprintable parts, and we call these not cost-effective parts. These are parts that we recognize using machine learning. We classify them as screws, bolts, nuts, sheet metal parts. So we have machine learning algorithms that use Polygoninca I would say Polygoninca collects the data for us, and then using our data set and our our algorithm, we are able to categorize it in a very high precision. And once we know what's printable and what's not, we want to find the holy grail, which is where it actually saves money or has some kind of other benefit, which you can play with yourself and decide. I would like to show you how an analysis looks like. So this is an example of a printable part. We will give you the printability, the costs, the lead time, and the technology and material we chose for this example, obviously out of the technology and printer that interests your company or the printer that you have. And also we can take into account, what you think. So if you want to optimize for cost, you can optimize for cost. If you want to optimize for various material or other properties, you can do that too. And once we have that, we'll give you in detailed analysis from material analysis, what would the 3D printing material give you as opposed to traditional manufacturing, a geometry analysis. This is an area that we heavily use Polygoninca. This is not very interesting because it's printable, but let me show you a part with some issues. So what you see here is that we really have a huge range of tests we do. Some of these are basically taken from Polygoninca, for instance, hole recognition, thread recognition, etc. But I would say that the great majority are proprietary algorithms of Castor, where we use Polygoninca as the input for us. It's a great shortcut for us. For example, the wall thickness is not the one we're using that Polygoninca supplies. We also have an aspect ratio functionality into it, but it was a great shortcut for us and very reliable. And obviously, if we have any problems, we can use the Polygoninca mesh healing feature in order to get a new STL. So this is another area where we heavily use the tools. The next, we go to a cost analysis where we find the break-even point between traditional and additive manufacturing. Our costing model is very robust, but I will say, without going into too much detail, that both for traditional and for additive, we have various algorithms that Polygoninca help us solve. Then we go to lead time, a similar analysis is for lead time. And finally, we have a anisotropic material stress analysis to kind of give you the first indication if this is a good candidate for 3D or not. The last thing in this page I would like to show is that often our customers, especially in certain industries like aerospace, are interested not in what can be 3D printed as is, but where you'd get the most benefit from redesigning for additive. So the first example is our patented algorithm called part consolidation. And in it, what we do is we look at an assembly as a whole, and we look for those parts that are manufactured separately, probably because they are designed for different manufacturing methods, but with AM, you could print them as one single part. This is the algorithm we use with HP in the example I showed you before. And again, this is another example of an algorithm that would not be possible without TechSoft help. And finally, weight reduction. So there are many companies out there that are much better in generative design than we are, but what's unique to us is that we are able to scan thousands of parts and find those bulky parts that it would make the most, you'd get the most value if you go into redesign a project. And I think this is novel because there isn't really a data-driven approach to choosing these parts, and sometimes we are working with huge machines, and a mistake in this decision could reduce the impact from something small to something that can be a game changer for whatever you're trying to build. So that is my quick demo. I would be very happy to answer questions.
All right, excellent. Thank you, Elad. That was a fantastic demo. You're doing some great things with that rich data and those powerful tools from Polygonica. Thank you so much for sharing that. Here's an opportunity for questions as well. Where can you find more about these technologies? We encourage you to go to techsoft3d.com, Polygonica, or 3dcastor.com. TechSoft does have a tight partnership with Polygonica and MachineWorks. We are the sole reseller of the Polygonica SDK worldwide. We're happy to work with you. Richard's happy to work with you as well. It's up to you, but you can fill out a form on either of our websites to evaluate this SDK. You can go to techsoft3d.com to learn more about our other additive tools, and then also 3dcastor.com to learn more about them. We do have a few minutes remaining and a few questions, and we're going to put Richard in the hot seat to answer a few around Polygonica. So we'll give him a minute to compose himself.
Oh, no, I'm good. I've been reading the docs while I've been talking.
So the first one, do you have a database of lattice structures? So you did show us the generation of a lattice structure. Where does that come from? And can they be customized? Yeah, so short answer is no, we don't. I mean, Polygonica is really a quite low level mesh library. Mm-hmm. So the lattice I was showing you there was just created by the demo program, but it uses the functions within Polygonica, such as obviously healing, offsetting Booleans, creation of geometry, multi-Boolean union, simplification and remeshing. All of those are relevant and really quite useful. And it's great to have fast, robust, mesh-based algorithms to do that stuff. But the actual, we're not additive manufacturing experts. We don't know where to put a lattice, how to make a good lattice structure. That's our customer's job. They're the experts in that, and the same with supports as well. So you can take our tools and then generate your own IP that's unique to your software or your printer or whatever in terms of lattices and supports. So sorry, there isn't actually a database of ready to go things. Yeah, thank you. And then the second part of that question, is it customizable? So since you have all these tools, is it possible, right, to insert any lattice that you may have access to? Yeah,
sort of by definition. I mean, there's no. There is something that creates a lattice for you in Polygonica, but it's not really a lattice. It's just a bunch of polylines. It's really, really fast polyline clipping. So there's no 3D lattice creation API in Polygonica. So in terms of customizing it, yes, you can customize it because you've got to create it.
Great. Yeah. And then another question about Polygonica. You showed us the slicing.
Yeah.
What kind of parameters are available as part of that slicing API?
Yeah, so that's a good question. So first of all, there's two variants of the slicing. One works in memory, and one is there in case you're going to run out of memory, which is quite common on large printers. Lots of parts on there, and very, very, very tight tolerances. So you can make a decision to set off in memory or not. And then basically it's how many slices do you want and where do you want them? You define that, and Polygonica generates them for you. I mean, it's generating them by doing an intersection with the mesh. So the vertex coordinates on the slices are coming from that intersection of the plane with the mesh. You can do it in any orientation, as many as you want, etc., etc. There are some more let's call it arcane things in there where you can hook up callbacks in the slice process to do various things. Yes, you can specify the height of the layer and slice. Yes, so I mean, basically, when I say you can basically define what the slices are and where they are. So if you want to have slices where the height increases in a Fibonacci series, you can do that. Yeah, it's your choice basically. So orientation, starting point, distance between slices, all that kind of stuff. It's a we see it as a geometric operation, not as an additive manufacturing thing. So we provide you with that ability. Okay, thanks for saying thanks. People don't often say that we've answered the question, so thanks for that.
Yeah. Well, very good. We have another minute maybe for any other questions. Thank you for those. Those were fantastic. And thank you everyone for being with us today. Thank you, Richard, for your presentation, and Alad as well for joining us.
No problem. I just want to add one thing that when choosing these kind of heavy tools, I think just as important as the tool itself is the kind of support you would get. And I must say that I'm bugging these two guys and their teams on a weekly basis, and I'm getting quick responses. And I even had a few features designed especially for me. So yeah, that's something you should take into account too.
Yeah, great. Thank you.
Yeah, thank you very much. It's great to work with you also.
Yeah, it doesn't look like we have any other more questions coming in. Thank you everyone for joining us today. We hope to engage with you either virtually or in person at one of our events coming up later this year. We will be sending out a recording of this, so you can share that, rewatch it, do whatever you want. And if you do have any questions, please reach out to us through our websites. You can contact us there. Also sign up for a free evaluation to test these SDKs out for yourself. Well, again, thank you everyone. Have a fantastic afternoon, wherever you may be, morning, afternoon, evening. Thanks again, guys. It was a great working with you today. Take care, everyone.